All right, let's look at a way to simplify some equilibrium problems so we don't have to worry about quadratic equations. Now, this doesn't work for all equilibrium problems, but it will work for some. All right, what we're going to do is on our first method of looking at it, we're going to make an approximation that affects the answer a little bit, but we will be comfortable with the amount that affects the answer, because what we will find is to the significant figures of the problem, you essentially will get the same answer as putting it in the quadratic equation. And this can be done if the initial concentration of a reactant is large enough, 0.1 molar or greater, and K is small enough, 1 point, like 1 times 10 to the minus fourth or smaller value for K. 1 times 10 to the minus fifth, 1 times 10 to the minus sixth, or even smaller. And the way it's going to work, if you recall from the previous video, we got in this problem of the quadratic equation, and truthfully the problem came from this point right here, when we had to take 0.10 minus 2x, and because of this 2 here, we had to square it. That gave us a squared term. And what we're going to find out is this is common when you have a number like 0.1, the initial concentration, minus value x. That's what makes things rough in our calculations. So, is there a way we can get rid of this? Just note for clarity here, in this problem, our equilibrium constant is 0.36. So the shortcut I'm about to tell you would not work for this one, because I need that k to be smaller than 1 times 10 to the minus fourth. And this is not. So with this one, man, you just have to go through the quadratic equation. Now, with computers and whatnot that we have, you can actually just plug in the value into a computer, the A, the B, and the C, and if you put it in right, you can get that calculation pretty quick. But still, it is a pain, so let's try to not deal with that pain. So, simplifying our equilibrium problems. What we're going to do, if our initial concentration is large enough, 0.1 molar or greater, and our K is small enough, 1 times 10 minus fourth or smaller, we are going to assume that that initial concentration minus X that we'll get from our ice table is essentially going to be equal to the initial concentration. We're going to assume that this X value, the value for X that we're subtracting from the initial concentration, this value for X is so small that it really does not affect the initial concentration value. That's the assumption we're going to make. Now, if our K is less than 1 times 10 minus 4, this is usually a safe assumption. So let's go looking to see what we can find. Here is an example problem. Let's look at the reaction of A in equilibrium with 2B. The equilibrium constant is 3.3 times 10 to the minus fifth. What are the equilibrium concentrations when the initial concentration of A is 1 molar? Okay, two things I'm looking at. My initial concentration greater than 0.1, check. K is less than 1 times 10 to the minus fourth, check. So this is a good problem where we can take our shortcut. We can make our assumption that this X is negligible compared to the initial concentration. We can ignore minus X. So, well, we've got an equilibrium constant. We need to calculate equilibrium concentrations. That means ice table. We write the reaction. ICE line. Initial concentration of A is 0. Initial concentration of A is 1.0. Concentration of B is 0. Minus X plus 2X. Remember, because I've got two B's forming for every one A that disappears, so that's plus 2X. So at equilibrium, we're going to get 1.0 minus X and 2X. Plugging these into the equilibrium constant expression, I always recommend at this point writing it down, so you remember to get that squared term in there. 3.3 times 10 to the minus fifth, our K value, equals 2X squared, because we have the squared term here, divided by 1.0 minus X. All right, and working this out, we find that we get 3.3 times 10 minus fifth equals 4x squared, because 2x quantity squared is 4x squared, divided by 1.0 minus x, and we realize we're going to have an x squared term, we're going to have an x term, and a number And this is just going to be a quadratic equation, and that's going to be nasty. But because we've met our conditions of K and initial concentration, let's assume that X is very small compared to 1.0. If X is very small compared to 1.0, then 1.0 minus a very, very small number is still essentially 1.0. Which means I can simplify this equation into 3.3 times 10 to the negative fifth equals 4x squared divided by 1.0. And the math becomes very easy now because to solve for x, you just multiply this by 1, divide it by 4, and square root the answer. All easily done on the calculator. You find x is 2.872 times 10 to the negative third. Note, for significant figures, our k value, our equilibrium constant, has two significant figures, so our answer must have two significant figures. That means our answer should be 2.9 times 10 to the minus third. I carried out more significant figures just to demonstrate what's going to happen in a little bit. Okay, now plugging this value in for x for our equilibrium concentrations, get concentration of A is 1 minus x, 1 minus 0.00287, which is 0.9971. Round that to 2 sig figs, we get 1.0. So making our assumptions that 1.0 minus x is 1.0 turns out pretty good. Concentration of B is x squared, and we get to 2 sig figs 8.2 times 10 to the minus 6th molar. And you might be saying, well, yeah, but we made this assumption that 1.0 minus x is 1.0, so we ended up with that answer. Wasn't that the assumption we made? Yes, it is. But we made it based on our fact that we knew x was going to be very, very small because our k, our equilibrium constant, was very, very small, meaning this reaction does not lie to the right. At equilibrium, we have much more reactant than product, so we knew the concentration of x would be small. And just to prove it to you, I plug this into a computer program that calculates quadratic equations because it's just too nasty to do on your own in this day and age. Using our shortcut, we got 0.02872, which rounded up to 0.029. If you use the quadratic equation, you'd find x is 0.00868. Instead of 72 at the end, it's a 68, but it still rounds up to 0.0029. So using this shortcut got us the same answer to the proper number of sig figs without having to resort to any quadratic equations or anything like that. Okay, that's the first way of simplifying these problems. We're going to use that quite a bit in the next chapter on acids and bases. There is another way where if your K value, your equilibrium, you just don't think it is quite small enough. You're like, you know what, this makes me worried a little bit. For example, let's look at this. When you have that's the case, you can use something called successive approximations. When your equilibrium constant isn't quite small enough to make you comfortable. So here's our example. A is in equilibrium with B plus C. The equilibrium constant for this reaction is 1.0 times 10 to the minus third. Our initial concentration is 0.10 for A. Well, that 0.1 is fine. I'm okay with the 0.1 there, but 1 times 10 to the minus third, I would much prefer that to be 1.0 times 10 to the minus fourth or smaller. So I'm a little, this is just not quite small enough to be comfortable for me with my answer. I know my answer is going to be pretty good because that's still a pretty small number. This reaction does lie well to the left, and therefore I would not expect to have much product with that equilibrium constant, but can we really just ignore the minus x? Well, let's dig down through it. I need to know the equilibrium concentration, so A is in equilibrium with B plus C. Initial concentration of A is 1.100. A is going to go away, minus x plus x plus x. We got 0.10 minus x, x, and x. Here is my equilibrium constant expression for this reaction, plugging in my values. 1 times 10 to the minus third equals x times x, which is x squared, divided by 0.10 minus x, and we get this equation down here. And we're like, okay, we're on quadraticsville again. We're going to have an x squared term, an x term. Oh, this is going to be nasty. Can we ignore this minus x here? I'm not so sure if we can. But what I'm going to do is I'm going to do it anyway. I'm going to do it anyway, and then I'm going to work with my answer. So let's do that. Let's assume that the 0.10 minus x is essentially 0.10. Let's assume that this x value is going to be so small that to 2 sig figs, it's small enough that 0.1 minus that number is still going to be 0.1. All right. So when I do that, just like we did in the previous shortcut examples, I get x as 0.010. And these are the numbers I would have gotten if I'd plugged this answer into these values. But I'm not quite done there yet because okay, 0.10 minus x, 0.10 minus 0.10 minus 0.010 is 0.09. And to 2 sig figs, 0.09 is not 0.10. This is off by about 10%. And that's a little, I just don't like that. That's a little too far off for me. And I figured that would happen because I know that my k value is just not quite small enough. However, one thing I also know is when I did this approximation, when I assumed 0.10 minus x is 0.010, I assumed that x was so small that it was essentially 0 compared to 0.1. I now know that this number here is a better value for x than assuming it's 0 here, than completely ignoring it. I'm not going to completely ignore it. I'm going to run this calculation again. Instead of ignoring the minus x up here, I'm going to put in this value for x, which I know is not quite right, but it's pretty close to the right answer. So if I put in this value up into this equation, just plug my value for x that I got for the minus x part. Recall, you can't plug it into the x squared part, only the minus x part. So that gives me 1.0 times 10 to the minus third equals x squared over 0.10 minus x. 1 times 10 to the minus third equals x squared over 0.10 minus 0.010. The x I got here, because I know that this value for x is better than just ignoring it. This value, plugging this value in for x here, gives me a better answer than just ignoring that minus x. So when I do that, I get a value of 0.0095. All right, I now know that my first value for x was 0.01. 0.0095 is a better value, is closer to the right value of x, because I put it in this equation, and that made this equation a little bit better, a little more accurate. But I'm not done. What I'm going to do now is say, okay, I've got this new value for x. I'm going to plug that in again. I'm going to plug in this new value into that minus x. 0.10, or 1.0 times 10 minus third equals x squared over 0.10 minus 0.0095, because I knew my 95 was better than my 0.01, which is better than ignoring it. And when I work this out and calculate this x, I get 0.0095 to 2 sig figs again. Realize, well, now I can stop. Since I got the same answer as before, if I put 0.0095 back in here, I'm going to get 0.0095. With these successive approximations, each answer I get is closer and closer to the right answer. And when I get an answer for x, plug that in, and get the exact same answer, I know I've got the right answer. And so instead of 0.0090 molar for A, the correct answer would be 0.091 molar when you do the math, and B and C are 0.0095 molar instead of 0.01 molar. And if you're interested in how good successive approximation works, if you'd have just gotten to here, made your quadratic equation, plug those numbers in, you would have gotten 0.0095. So these successive approximations work nicely when your k value isn't quite small enough. If it's 1 times 10 to the minus third or 1 times 10 to the minus second, it's just not quite small enough to make this assumption, ignoring that minus x. But you do it anyway, get better and better values, and you end up with a good answer. Note, if this k value were like 0.3 or 0.6 or something like that, then successive approximations don't work. They actually bounce you back. You get two values for x bouncing back in between two numbers. It just doesn't work well. But if you're like, oh man, that's just 10 to the minus third, I don't feel comfortable making this approximation down here, then do the successive approximations. Do it anyway and plug that better answer in for x until you come up with an answer that doesn't change anymore. That will give you what the quadratic equation gave you.